Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to help you out with number 27 in your Unit 1 homework here. So let's see, a total charge Q distributed uniformly along a length L, consider the Gaussian surface shown. So we're looking at a charge distribution where, a charge is distributed along a line. The first thing I probably would do is recognize this, that there's a linear charge density. We usually denote that with the letter lambda, and you can get that by taking total charge divided by the total length. This is true because the charge is uniformly distributed along the length L. This will show up later in this problem. Now, the Gaussian surface already drawn for you, and what we're going to do is apply Gauss's law to this Gaussian surface. So whether you write in summation form or integral form, right, Gauss's law is basically this: the total electric flux, which is the integral of E dot dA. That's the E dot dA is the flux through any little surface. Again, this means that circle means over the entire surface, right, is equal to 4 pi k times the charge inside the surface. So what you need to do now is you need to apply this integral to all three surfaces. Let me call this surface 1, the side surface. Well, let me do the surface on the right, call that one 2, and then this surface 3. Now to do that, draw normal vectors, because remember the dA vector, right, what is that? It has a magnitude of area, but it's in the normal direction. Draw normal vectors on surface 1. Draw another normal vector here on surface 2. Then draw at least one normal vector somewhere on the side surface here, this surface right here. And then ask yourself, what is the angle between the electric field and the normal vector at each location? Now to do that, you also have to know something about the electric field vector. Now, if I pick a spot, I'm just going to pick a spot like maybe right here. Actually, let me color code, put a little color on that. All right, so I'm just going to pick a spot right here. I know it's not even on the surface, but humor me for this discussion. And remember how electric fields work. All right, the electric field due to a point charge is kq over r squared. Now, I know that this is not a point charge, but just humor me for the discussion. You could think of this line of charge as a bunch of little point charges. Okay? And electric field contributions due to each point charge, right, are given by this formula here. And again, the r squared in the bottom, it's very sensitive to distance. Now, what does that mean? The electric field here is due mainly to this stuff, the stuff that's close. And that should tell you roughly what is the electric field direction right at that point, or right on this point right here, or here, or here, or here. Then you ask yourself, okay, what is the angle between the electric field and the normal vector? And that will tell you something, I'll just say, about the flux through these three surfaces. Right? So this integral is going to have three terms to it, like boom, 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 because there's three surfaces over here. And two of those surfaces will have a very, very simple numerical value, I guess, but I'll let you conclude what that is. Then, another thing you have to consider now, when you do the side surface, again, you have to think about the electric field and its angle relative to the normal. And also then ask yourself, as I move around this surface like this, do you expect the electric field to change, yes or no? And depending on your answer, that will tell you if this electric field magnitude is constant on the integral. So that's pretty much how to handle the left-hand side. I don't want to get too much more into it as it's your homework problem. The right-hand side of Gauss's law, really it's all about this. So I'll just say the following. Look at the picture. Remember, we have a charge density equal to this, which has units of coulombs per meter. And then our Gaussian surface has a length labeled as little l here. Think about how you take this, what you mathematically have to do to it with this to get the charge inside the surface. So that's about as much as I think I care to say about number 27. Hopefully that's enough to get you through that problem. Have a great day.